This video we're going to look at hyperbolic functions. Hyperbolic functions can be found from the exponential function e to the x, and they're similar to your circular or your trig functions. So we already know that cos x is equal to e to the ix plus e to the minus ix all over 2, and sin x is equal to e to the ix e to the ix minus e to the minus ix all over 2i. So where they come from is these two things. So we know that e to the ix is the same by your rulers, is the same as cos x plus I sin x. Then for by de Moivre's then, e to the minus ix would be cos of minus x plus sine of minus x, which is the same as just cos of x plus I sin of x. And then what we can do is we can add those two things. So if you add this thing and the thing above, the e to the ix, what you would get is e to the ix plus e to the minus ix is equal to 2 cos x, and that means 1 cos x would be equal to e to the ix plus e to the minus ix all divided by 2. And a similar thing can be done then if you subtract them. You will get you'll get e to the ix minus e to the minus ix is equal to 2I sin x. That means to get sin x on its own, it's going to be e to the ix minus e to the minus ix all over 2i. So that's where they come from. So if you know these things, here in yellow, it's very easy then to get the new hyperbolic functions. So there's other names for these things. This one, for example, is called cosh. But I'm just going to call them hyperbolic cos, hyperbolic sine, hyperbolic tan, hyperbolic cosec, and so on. Just makes it easier. It's a bit of a mouthful, the rest of it. Okay, so hyperbolic cos then, very similar to the one we have here. So hyperbolic cos, similar to its circular or its trig function, is just e to the x plus e to the minus x over 2. And hyperbolic sine is e to the x minus e to the minus x all over 2. So those are your basic definitions, and then from them you can get your other ones. You can get your hyperbolic tan, your hyperbolic sec, your hyperbolic coth, and your hyperbolic, what have I not said, hyperbolic cosec. So hyperbolic tan, a couple of ways of writing it, and it's similar to a normal regular tan. Hyperbolic tan is hyperbolic sine divided by hyperbolic cos, which is this over this then. The 2's will cancel out. And what you could do as well, sometimes it makes it a wee bit easier, as we'll see later on. You could change that by multiplying through by e to the x. So if you multiply every term by e to the x multiplied by e to the x gives you e to the 2x. E to the minus x multiplied by e to the x gives you the 1. And e to the x multiplied by e to the x again gives you e to the 2x. And e to the minus x multiplied by e to the x gives you the 1. So that's another way that you could write your tan. Okay, you could also multiply through by e to the minus x and get a different looking thing as well. But I would learn one of those anyway. One of those ways, probably the top one, is the easiest one to learn. Okay, hyperbolic sec is the same as 1 over hyperbolic cos, and similar to your regular circular functions. If you look at the third letter of those, our third letter of sec is a c, and then that's why you know it's 1 over cos, because the first letter of that is 1 over cos is c. Likewise, hyperbolic cosec, the third letter is an s, and that's 1 over your hyperbolic sine. And this one, hyperbolic coth, the third letter is a t, and the first letter is a t. So there's a nice way of remembering. So you've got those definitions as well. Okay, and you can see where they exist as well. So the first ones, they exist for all x belonging to the reals. This one, and first and second, hyperbolic cos and hyperbolic sine exist for all x belonging to the reals. And tan exists for all x belonging to reals. This one, hyperbolic cosec, will not exist whenever x is equal to 0. So if you think about what happens when x equals 0, when x is equal to 0, this term here, this would just become a 1, and this would become a 1. So what you're going to have is 1 minus 1, which is just going to be 0. You're going to get a 0 on the bottom line. Basically, in mathematics, you get a 0 on the bottom line. That's a problem. Likewise, for this bottom one, x equals 0, you'd have 1 minus 1, so you're going to have a 0 on the bottom line. Again, that's going to be a problem. So that's why those two just don't exist. Keep it really simple. That's why they don't exist when x equals 0. So if you're plotting these things as a graph, that means there must be a discontinuity at x equals 0. X equals 0, remember, is just your y-axis. So your y-axis is going to be an asymptote. Okay, right. Oh, I forgot to rub this all out. Graphs of the hyperbolic functions. First of all, this is just going to show that the graphs of hyperbolic functions, and it's good to know if something's odd or even. So if something is odd, it will have rotational symmetry about the origin. If something is even, it will have line symmetry about the y-axis. So if we look at hyperbolic sine of minus x, we just put minus x into this thing. So this means you just replace your x with a minus x everywhere. That's what you end up getting. So you get this, which then just tidies up to be this. And then we could write that as minus of that. So really, hyperbolic sine of minus x is the same as minus of hyperbolic sine of x. So hyperbolic sine is an odd functions. So it gives it rotational symmetry about, that's very hard to read there. Let me write that out again. Rotational symmetry about the origin 0, 0. Okay, so just explain what that means. The simplest odd function we have is y is equal to x cubed. And there's y, what y equals x cubed looks like. So you can imagine this bit could be rotated through 180 degrees and it would fit onto this bit, and vice versa. This bit could be rotated through 180 degrees and it would fit onto this bit. So that's what your rotational symmetry about the origin means. So that's typically what an odd function will look like. Okay, so we know that when we're going forward. Same idea we're going to do with the hyperbolic cosh. Hyperbolic cosh of minus x, put in the minus x, and what you end up getting is that hyperbolic cosh of minus x is equal to this thing, and this sure is the same as just hyperbolic cosh. So that shows you, so hyperbolic cosh is an even function, i.e. it is symmetrical about the y-axis, and I'll just explain what that means then. So again, the most simple even function is y is equal to x squared, and that's what y equals x squared looks like, and this bit could be reflected on the y-axis to give you this, and vice versa. You could reflect this bit on the y-axis to give you this. Okay, right, these graphs in. So if we want to sketch, first of all, we want to sketch y is equal to hyperbolic cosh of x. The first thing we want to do is we want to sketch what it is made up of. So hyperbolic cosh is made up of, first of all, it's made up of e to the x, and it's also made up of e to the minus x. So that's what those two graphs look like. Now look at what hyperbolic cosh is. Hyperbolic cosh is this thing here. So it is e to the x plus e to the minus x. Now both of these graphs go through 1. So if you just pick a few basic points, so pick this point here, add e to the x plus e to the x, that point, you're going to have 1 plus 1, which is 2, and divide by 2, that's why that's going to be going through 1. And also, we know it's an even function, so it's going to be symmetrical. So if you pick this point, for example, if you add that point and that point, you're going to get a point which is above the 1, and then it's going to be going upwards as well, and then it's even, so it's symmetrical about the y-axis. So there's how you can see that's what has led me, that is what has led me to my e to the x. So I'll just highlight that is what has led me to my hyperbolic cosh of x. So there's what it looks like. Okay, the other one, so your hyperbolic sine of x, it is made up of, hyperbolic sine of x is made up of, again, this graph, but you're taking away this graph. So remember what hyperbolic sine of x is, it's this thing. So let's think about the most basic point then, the point when x is equal to 0. So when x is equal to 0, you're going to have e to the 0 minus e to the 0, which is 1 minus 1, which is 0, divided by 2 gives you 0. So that's where this first point comes from. And then again, we'll just worry about the right-hand side of it here. So we'll think about this point again here. Think about this point and this point. So you're subtracting those two things. So top one minus the bottom one. So it's going to be definitely it's going to be smaller than your hyperbolic cosh. So that's why it takes that sort of shape. So it's going to be smaller all the way along. And then remember, it was an odd function, so it has that rotational symmetry about 180 degrees. So all of those things come into play for you to draw it. If you don't like that, what you can do is you can just learn them off, and that will work absolutely fine as well. Okay, next thing we're going to look at is your hyperbolic tan. And first of all, we see when x is equal to 0, hyperbolic tan is going to be equal to 0. So that's just going to be 1 minus 1 over 1 plus 1, which is just going to be 0 over 2, which is just 0. So that's why when x equals 0, hyperbolic tan is 0. We're also going to look then at, see if it's odd or even, see what's happening with this thing. So hyperbolic tan of minus x is e to the minus x minus 1 over e to the minus x plus 1. You could multiply those things through by e to the 2x, and that gives you 1 minus e to the 2x over 1 plus e to the 2x, which is the same as minus hyperbolic tan of x. So hyperbolic tan of minus x is the same as minus hyperbolic tan of x, which tells you hyperbolic tan of x is an odd function. So again, it's going to have that rotational symmetry about the origin. Right, another way of looking at this, talked about this earlier on, another way you could say is that hyperbolic tan of x is equal to, so from the basic definition, you can get to this one by dividing through by e to the 2x. Now it just makes it a wee bit easier for me to see. So as x tends to infinity, e to the minus 2x tends to 0. So that means hyperbolic tan of x tends to 1. So the reason for that is you can have 1 minus 0 over 1 plus 0, which is just 1 over 1, which is just 1. All right, and then looking at the other one, as x tends to minus infinity, so it tends to minus infinity, e to the 2x tends to 0, so this bit tends to 0, and this bit tends to 0, so what you're really just left with is 0 and 0, so you've got minus 1 over plus 1, minus 1 over plus 1 is just plus 1. So that's what you have got. So you know, as x tends to infinity, hyperbolic tan of x tends to plus 1, and as x tends to minus infinity, hyperbolic tan of x tends to minus 1. So that's what your graph looks like. So first of all, it goes through 0, it tends to plus 1 as it tends to infinity, it tends to minus 1 as it tends to infinity, and also it's got that rotational symmetry about the origin. So if I rotate that 180 degrees, I will get that. So there's a few things for us to do. And also 1 and minus 1 are horizontal asymptotes to the curve. Okay, this next one, it says sketch hyperbolic sec for x belonging to the set of reals. Now remember what hyperbolic sec is. Hyperbolic sec is the same as 1 over hyperbolic cos, and remember hyperbolic cos itself is even, so that means hyperbolic sec is even, so which means it's symmetrical about the y-axis, so it's got line symmetry about the y-axis. Also, we know hyperbolic cos is always greater than or equal to 1. We know that from this graph here. There's your hyperbolic cos in yellow. It's always greater than 1, which means greater than or equal to 1, I should say. So the smallest that sec can be is whenever hyperbolic cos is equal to, the biggest that sec can be is whenever hyperbolic cos is equal to 1. Because 1 divided by 1 gives you the 1. And then if sec's bigger than that, if hyperbolic cos is bigger than that, then sec will be smaller. So say, for example, hyperbolic cosec was tending to infinity. That means your hyperbolic sec is going to tend to 1 over infinity, which means it's tending to 0. So it's getting incredibly small. It will never actually get there but it is going to be very, very small. So that's why your graph looks like this. We'll just do the right-hand side. When it's 0, at x equals 0, hyperbolic cosh is 1, and 1 divided by 1 is just 1, and then it's just going to get smaller and smaller and smaller. And remember, it's symmetrical because it's even, so it's out here as well. Okay, so there's ways you can piece through that. Not easy, I don't think, but definitely you can do that. Okay, right. I'll show you this one. So I had that all done out already, shouldn't have. It says find the exact values of x for which hyperbolic tan is equal to 1. So when it says exact values, this is what you want to do. If it doesn't say exact values, use your calculator. If you press your hype button on your calculator, then it brings up options of doing inverse hyperbolic tan and inverse hyperbolic and so on. So hyperbolic cosh and so on. But that's what you want to do. But if it says exact, you've got to go back to the basic definition. So what we're going to do is, from this bit, we're going to do a wee bit of cross multiplying. So we're going to say e to the 2x, 2 times e to the 2x, 2 upon e to the 2x minus 1 is equal to 1 upon e to the 2x plus 1. And then just multiply out, that's 2 e to the 2x minus 2 is equal to e to the 2x plus 1, which means e to the 2x is equal to 3. And then what you could do is take natural logs of both sides. So you're going to get 2x is equal to ln of 3, which means x is equal to a half ln of 3, which is exact. That's an exact answer. Okay, lovely question. Okay, the next one. Again, I've written this out, apologies. Okay, for the next one, we want to prove that hyperbolic cos of x squared minus hyperbolic sine of x squared is equal to 1. Very, very important. We identity it takes us on to something. Okay, we're going to prove this from the basic definitions. So hyperbolic cos of x, remember, is e to the x plus e to the minus x, and that's all over 2, but it's squared, so that's going to be squared, and the 2 is going to be squared to give you 4. Hyperbolic sine of x, remember, is e to the x minus e to the minus x, and it's hyperbolic squared. So that's what you've got. So let's just work through this and see what we get. So we do this out, you're going to have a quarter times e to the x plus 2 plus e to the minus 2x. Sorry, that should be e to the 2x plus 2 plus e to the minus 2x. Then minus, again, a quarter. And that's going to be e to the 2x minus 2 and then plus e to the minus 2x. Right, I'm just going to show you where this minus 2 comes from. This might have confused you a wee bit. If we did this out the long way, you've got your e to the x times e to the x. That's going to be e to the 2x. And then you've got e to the x times e to the minus x. That would just be a 1. Likewise, you've got that again. That's another 1. And then the last one, you've got this. That's going to be e to the minus 2x. So you can see where that 2 comes from. Similar on the other one. If you did that out the long way, I sort of skipped that out there. Apologies. And okay, all we have to do now is tidy this up. So what you've got, let's just look what you're going to have. You're going to have a quarter of e to the 2x, then minus a quarter of e to the 2x. And then you're also going to have, we'll do it in blue, you're going to have a quarter times 2 and a quarter, and then minus a quarter times minus 2. So what you have really is 1 quarter times 4. And then in green, you have a quarter times this thing, and then minus a quarter times this, so they cancel each other out. So all you have got is a quarter times 1, which is equal to 1. So QED, which just means you've shown it's been solved. Okay, now let's have a look at this then. Since we've got that definition, that hyperbolic cosh squared minus hyperbolic sine squared is equal to 1, then you can get through to these ones. So where you get these, I would only ever learn this one, to be honest. Just like the circular ones, I only ever learn cos squared plus sine squared equals 1. Learn this one off, and then you can get to the other ones. So how we've got from here to here is we've divided through by hyperbolic cos squared, and how you've got from the first one to the last one is you divide it through by hyperbolic sine squared. So that's really what I would be doing, and then you can get those other two identities. So again, I would learn the first one, and then I would know how to get the second one and the third one. Okay, next one. It says prove that hyperbolic cos of x plus y is equal to hyperbolic cos of x plus hyperbolic cos of y plus hyperbolic sine of x plus hyperbolic sine of y. And we're going to have to prove this through the identity. So I have done this out already, so I'm hopefully this is okay just to go through it like this way. We're going to look at the right hand side. The right hand side is a quarter upon, now where this comes from, this quarter, remember what this is. This would be e to the x plus e to the minus x all over 2, and this would be e to the y plus e to the minus y all over 2. So when you do that, the 2 times the 2, you get the quarter. Likewise for this. So what we've got here, the quarter sorts out the half and the half, and then this is the top line of hyperbolic cos of x, this is the top line of hyperbolic cos of y, this is the top line of hyperbolic sine of x, this is the top line of hyperbolic sine of y. Okay, so your quarter's still here, and then you're just doing your curly lines. So e to the x times e to the y is e to the x plus y, e to the x times e to the y, e to the x times e to the minus y is e to the x minus y. You've also got this, e to the x times e to the y, e to the minus x times e to the y, and e to the minus x times e to the minus y. So there we've multiplied out those 4 things there. Next bracket, you've got e to the x times this, e to the x times this, minus e to the minus x times this, minus e to the minus x times this, and again, this is where these 4 terms come from. Now it's just tidying up, and you can tidy up and we can see what you get is a quarter upon this thing, and then that 2 can come outside, so the 2 comes out with the quarter. 2 times a quarter is just a half, and then you're left with e to the x plus y plus e to the minus xy, and that is the same as hyperbolic cos of x plus y. Okay, and note, similar to how you got your double angles for your trig functions, you can find as well, by writing x is equal to y is equal to a, you can get hyperbolic cos of 2a is equal to hyperbolic cos squared of a plus hyperbolic sine squared of a. Okay, last page for these notes. And again, find an identity for sine 2a in terms of hyperbolic cos of a and hyperbolic sine of a, and hence find identity for hyperbolic tan of 2a. So hyperbolic sine of 2a, how we do this, similar to what we've just said, you let your x be equal to 2a. So that's a half upon e to the 2a minus e to the 2a, so minus e to the minus 2a. And this is the difference of 2 squares. So where this next line has magically appeared from, you have x squared minus y squared. That's what you have in your first line. And then that's equal to x plus y, and x minus y. So that's where your first line is equivalent to x squared minus y squared. Second line is equivalent to x plus y, x minus y. So that's where we've got to now. And then this is the same. You could write these both as something over 2, which means you've got an extra 2 on the bottom line. So what you need to do to cancel that out is multiply by a 2 outside. So what you really have got is 2 times hyperbolic cos of a times hyperbolic sine of a. And we're just going to write that differently because we learned that differently for circular trig functions. So write it as hyperbolic sine of 2a is equal to 2 hyperbolic sine of a times hyperbolic cos of a. Now, we've already done this one. Hyperbolic cos of 2a, we did that one from the previous example. So hyperbolic tan of 2a is this thing divided by this. And then how you get to the next line, your last line I should say, is divide through by cosh squared. So divide through by cosh squared. So if you just think about this, the top, every term, you've only got 3 terms here. You've got this term on the top here. You've got this term on the top here, sorry. You've got a term on the bottom, the green, a weird green colour, and this one in orange. So these 3 terms, every term needs to get multiplied by hyperbolic cosh squared. So we'll do the 2 bottom ones, they're the easy ones. Hyperbolic cosh squared divided by hyperbolic cosh squared, it just becomes 1. Hyperbolic sine squared divided by hyperbolic cos squared becomes hyperbolic tan squared. And the top one, it's a tricky one. You've 2 bits. The 2 just stays, and the hyperbolic sine, divide by hyperbolic cos by hyperbolic cos, you'll get 1. And hyperbolic sine divided by the other hyperbolic cos gives you the tan. So that's where that comes from. So that is what you end up getting. So, right, let's have a look at these things and let's see if we can arrive at our, what's called the Osborne's rule, which is coming up. Now, let's compare these to their trig functions. So here, we have shown, what we have shown already, we have shown that, we'll look at this double angle one here. Hyperbolic cos of 2a was equal to hyperbolic cos squared of a plus hyperbolic sine squared of a. Now compare that with its circular version. The circular version of that, or the trig version, was cos of 2a was equal to cos squared of a minus sine squared of a. So it's very similar, except that the product bit, the sine squared bit, which means sine times sine, where it was negative, it turns to be positive. Okay? Likewise, if we look at our hyperbolic cos of x plus y, it worked out to be hyperbolic cos of x, hyperbolic cos of y, plus hyperbolic sine of x, hyperbolic sine of y, whereas this, the circular function of it was cos of x plus y is cos of x, cos of y minus sine of x, sine of y. So basically the Osborne rule tells you that for any product of sine or cos, any product of sine, it converts into hyperbolic sine by the hyperbolic version by changing the sign of it from being negative to positive, and vice versa. All right. So any product of sine, trig function sine, you will change from a positive to negative and vice versa. So let's look at that as well. Okay, this last one is very, very messy. Let me write that out again. We had hyperbolic tan of 2a was equal to 2 hyperbolic tan of a over 1 plus hyperbolic tan squared of a. Now let's compare that with its trig function. It would have been tan of 2a is equal to 2 tan of a over 1 minus hyperbolic tan squared of a. Now you think, well, why is this one changed? This was a minus and it's now changed to a plus. But think about what tan is. Tan is the same as sine over cos. So tan squared really is that times that. So there is a product of sines. You have sine times sine. So that's why the minus has to change to a positive. So what the Osborne rule tells you, the Osborne rule says the formulae for circular and hyperbolic functions correspond exactly, provided that the sign SIGN is changed whenever there exists a product or implied products of implied products. That's what I've done in this one. This was an implied product here because you have tan squared, which is it's not directly a product of sine, but it is really because you've got sine over cos in the tan. So that's what you've got. So the rule is to replace each trig function with its corresponding hyperbolic function, and change the sign of every product or implied product of two signs. So there's a couple of examples. So cos of 2a we knew was equal to 1 minus sine squared. So that thing would become hyperbolic cos of 2a is 1 plus hyperbolic sine squared of a. And tan of a minus b is equal to tan of a minus tan of b over 1 plus tan of a plus tan of b. So the only implied product bit is the bit on the bottom line. So you can see it changes to be minus hyperbolic tan of a upon hyperbolic tan of a. So the whole thing is tan of a, that should say hyperbolic tan of a minus b is equal to hyperbolic tan of a minus hyperbolic tan of b over 1 minus hyperbolic tan of a hyperbolic tan of b. So that is the end of that video. That was a fairly long video, but just work through that. Not too bad, all of it. A lot of just understanding really in that one. Not a wild lot you could be asked about.